Hi everyone. In today's lecture, we are going to be looking at light. So before we get into, and primarily what we're going to be looking at is light in relation to plants and plant growth and development. But before we get into that, we need to have an understanding of what light is. So light is a type of electromagnetic radiation, and all that is radiation or energy that is propagated through space in waves, right? And you can see if we look at our electromagnetic spectrum here, we have a bunch of different types of energy. I'm sure you've heard of all this stuff, right? Gamma rays, X-rays, ultraviolet, our solar spectrum or visible light, infrared, etc. And you can see this is just energy that moves through space in waves, right? And it's the length of waves or wavelength, which is the distance from crest to crest on your wave, right? That is going to affect or determine what type of energy we have, right? So if we have very short wavelengths, right, we classify those as gamma rays, right? As we get a little longer, it transitions to X-rays, ultraviolet, visible light, infrared, satellite, wireless TV, etc. Right? So that's important to know that the wavelength, right, or distance from crest to crest on waves, on your waves, is going to determine what type of energy you have. Now, if we're looking at the light from the sun, we see that our solar spectrum produces UV light, right? A little bit of UV light, lots of visible light, about 47%, and then lots of infrared light. Right, so that's what's being produced by the sun. Right, so we are in this solar spectrum right here. That's what gets produced by the sun. And then what's also important to know is that we see light, or at least in the visible light spectrum, we see light in colors, right, in terms of different colors. And again, it's the wavelength that is going to affect what color we see. Right, so on the shorter wavelength, shorter end of the spectrum, we have our violet and blue wavelengths, or violet and blue colors. And then that grades into green and yellows in the middle, and then red towards the longer wavelength end, right? So that's a pretty good background on light. Now, why is light important for plants? Well, this is adapted from Bruce Bugbee, who is a professor at Utah State University. He's got a series of YouTube videos. You can Google his or put his name into the search. He also is affiliated with Apogee Instruments. He's got a great series of YouTube videos on light and their effect on plants and other parameters. But he has these 9 cardinal parameters for plant growth, right? And you see them there: temperature, humidity, wind, carbon dioxide, in the root zone, temperature, water, nutrients, oxygen. And then at the top here is light, right? And light is incredibly important because it's really through light that plants are able to convert carbon dioxide into sugar, right? And that's through this process called photosynthesis. They use photons or energy from the sun and combine it with carbon dioxide and water, and they use it in this process to create one glucose molecule right there and oxygen as a byproduct. And this is important because it's this glucose that is then used as the energy source to grow the plant, or it gets converted into hundreds of other compounds that are used by the plant, right? And ultimately, photosynthesis, or the rate of photosynthesis, is going to determine the yield and quality of your vegetables or fruits that you are producing, right? Or maybe even flowers if you're growing flowers. All right, so because of this, light is extremely important, right? Because light is going to affect photosynthesis. It needs light to occur. And then photosynthesis is determining yield. So consequently, light is incredibly important for our plants. Now, that being said, we've already talked about that we have different wavelengths of light if we're talking about the visible light spectrum, right? And that really runs from 400 to 700 nanometers wavelength. So we have all these different wavelengths. Are they all equal for photosynthesis, right? Do they all drive photosynthesis the same way? Is one color of light better than a different color of light? Well, this work kind of started in the 1970s, right? And its experiments in the 1970s showed that chlorophyll absorbed a larger percentage of red and blue light and little green or yellow light, right? If you see here, we have peaks, and this is percentage of light absorbed by chlorophyll. We have peaks here for the different types, A and B, peaks here in the blue light spectrum, and peaks here over in the red. Now, this gave rise to the idea that plants only really use red and blue light for photosynthesis, and they don't really need green or yellow light or kind of these other spectra of light. And when we developed LEDs, we started growing plants under just red light or blue light or a combination of red and blue, and they didn't have the best results. And the question was why, right? Why, if they're just using red and blue light, why are we not seeing increased growth by growing under just these lights? And one of the problems is that those initial experiments done in the 70s just looked at chlorophyll. Now, chlorophyll is that pigment that absorbs light energy during photosynthesis, so it's incredibly important. But those experiments just looked at chlorophyll, right? They liquefied the leaves, extracted the chlorophyll, and they didn't look at the whole leaf in general. And one of the things that you see with blue and red light, because it gets absorbed so quickly, is that it doesn't really penetrate into the leaf very far, right? Or penetrate past the leaf. Now that is different with green light. And if you see here, this is the ability of this light to penetrate down. And you can see that green light penetrates much deeper than blue or red, right? And part of this is because our red and our blue is getting absorbed so quickly. So if we're looking at a leaf here, we're going to see that that red and blue light gets absorbed very fast and not much light is going to pass through that leaf. Now, if we have a plant that has multiple leaves and we have leaves up in the canopy and leaves below, not much of that red and blue light is going to be able to get below those initial leaves, so really get into deeper plant tissues. And that could have an effect on the ability of those, ultimately the rate of photosynthesis, right? If those leaves lower in the canopy are not able to access light, then they're not going to be able to photosynthesize as effectively, and we may have reduced growth, right? So that's one of the things that could be happening here. And then we also see, if we look at the rate of photosynthesis as a function of wavelength, we see even though that little light is absorbed in this green and yellow spectrum, we do see photosynthesis occurring at using those lights, right? And that is, part of that is there is some absorption, as we're going to see in a little bit. Green light is it's very efficient and when it comes to photosynthesis, right? So we're able to convert that energy very efficiently into chemical energy. And then there's also other pigments besides chlorophyll that also capture those other wavelengths of light as well, right? So just because we see here with those initial experiments doesn't mean that green light isn't useful, and some of that green light is captured and utilized for photosynthesis. And that's kind of what you see here with this McCree-PAR graph. So McCree did work, and he looked at each spectrum of light, or each color of light, and then he measured the fraction of that light energy that gets converted into chemical energy through photosynthesis. And you see here, you have from this McCree-PAR graph, you have your kind of local maxima here, or these, why can I not think of the word? We'll just say local maxima here at the blue and over towards the red. But you can also see that all these other colors of light or wavelengths of light are also utilized by our plants and get converted into chemical energy, or get converted ultimately into glucose, right? Now, this McCree-PAR graph gave rise to this idea of photosynthetic active radiation, and that's what that PAR stands for. And we've taken that now, or for a number of years, to be really wavelengths between 400 and 700 nanometers that you see here are the important wavelengths for photosynthesis, right? So that's when we're looking at wavelengths or color of light, it's these colors that are most important for driving photosynthesis, not so much UV, not so much infrared. Now, this is going to change when we get to the end of the lecture, but for largely, that's kind of what we've been going on for a number of years, right? So all the colors of light are important for photosynthesis. They all drive photosynthesis. That being said, how much light do our plants need? Well, if we look at light quantity, which is the measure of how much light is being produced, we have different ways of measuring this light. Now, historically, we looked at something called lumens, and this was the measure of light output that is visible to the human eye, right? And then we used that lumen measurement, right? So that's the light output that we could see. And we used that and we were able to quantify or to create two other measurements, foot candles and lux. Now, a foot candle is the amount of lumens shining on a square foot, and a lux is the amount of lumens shining on a square meter, right? So it's kind of like English and metric versions, right? So the 1 lumen is 1 candle, right? And again, this is developed back in the day, right? So 1 lumen is 1 candle. 1 foot candle is the amount of light that we see if we take 1 candle, set it a foot away from a wall, and we see that amount of light shining on a 1 foot by 1 foot square. That would be what we call a foot candle, or the intensity of light that we call a foot candle. Right? Does that make sense? Now, lumen, same thing, but just different measurements. We're doing metric, right? So we take our lux, we take our 1 lumen, we put it a meter away from a wall, and the amount of light that we see, the intensity of light that we see in a 1 meter by 1 meter square, we refer to as lux. And then we use these two measurements to quantify light quantity or light intensity of different lights that we saw. Now, the problem with this is that both foot candles and lux are based on lumens. And again, lumen is a measure of light output that is visible to our human eye, right? It's the measure of light that we see when a candle is lit, 1 lumen. But if we look at our PAR graph here, right? Remember, this is our photosynthetically active radiation from 400 to 700 nanometers. If we look at lumen, or the light that we see with our eyes, we could see that human perception of light is biased towards this green and yellow light, right? It's biased right towards here. We see very well, we see green light and yellow light very well. We don't see it as well, or we have less ability to quantify it when we're looking at darker blue light, so shorter wavelengths, and well as longer wavelengths towards the red, right? So if we're using lumens, we're looking at light from our perception, as opposed to plants that, as we saw, are utilizing this full spectrum. So this whole spectrum is important for plants, this photosynthetically active radiation, as opposed to just what we're seeing with lumens, which is right here. So because of that, we developed other methods of measuring light intensity besides lux and foot candles. And they are referred to as PPFD, or photosynthetic photon flux, and PPFD, or PPF and PPFD, photosynthetic photon flux density. Now, there is a little bit of, there's a little ambiguity in these terms. They are sometimes interchangeable, so you will see these, especially in older literature, they use photosynthetic photon flux. Sometimes they use photosynthetic photon flux density to mean the same thing. But in current day, and where we're going with it, is that photosynthetic photon flux, or PPF, is the measure of the total amount of PAR that is produced by a lighting system each second. And it is measured in micromoles per second, right? So remember, PAR is that range from 400 to 700 nanometers, that the spectrum of light that our plants use, right, for photosynthesis. And now if we take that and we measure, if we're looking at a light source, so a light or even the sun, how many micromoles or photons, essentially, think of it as how many photons of light within that range of 400 to 700 nanometers are being produced a second. And that is photosynthetic photon flux, PPF. Now, if we are interested in how much of that light is actually being produced or reaching a certain point, we're going to utilize photosynthetic photon flux density, right? And that is the measure of photons that are arriving at a surface each second as opposed to whereas photosynthetic photon flux is the amount of light that's being produced each second. Flux density is we're taking that amount of light that's being produced each second and we're measuring how much is landing on the surface of an object, right? So it's equivalent to when we talked about lux here or foot candles, right? It's photons of light that are landing on a 1 meter by 1 meter surface. And that's how we measure it, right? So it's really just taking what we looked at here with foot candles or lux, and instead of basing it on lumens, based on our visual ability to see stuff, we're basing it on the amount of photons of light within the spectrum that we can measure, right? So it's a more accurate version, especially when we're talking about plants. It's a more useful measure than foot candles or lux. So that being said, right, we kind of have an idea of how to measure light, or at least how to quantify it. It's that light is important for plants within that photosynthetically active radiation, so from 400 to 700 nanometers. Knowing all that stuff, how much light do our plants need? Well, we can kind of look over here on this left, and this is a general curve for most plants, right? And on this x-axis, we have our ppfd, that photosynthetic photon flux density, right, in micromoles per meter squared per second. And over here, we're going to have net photosynthesis, right? So how much photosynthesis is occurring. And you can see as you increase light intensity, right, here's 0 all the way over here, 500, 1,000, 2,000 ppfd. 2,000 is about a sunny day, what you're going to see outside. As you increase light intensity, you're going to see an increase in net photosynthesis, really up until a point, right? It starts to level off eventually. But especially in the beginning, you see this net increase in photosynthesis as you increase light intensity. And that makes sense, right? Our plants are utilizing those photons for that process. So the more photons you're getting, the faster and the more photosynthesis should be able to occur, is what we see here. We can also see that there is a baseline that just for that our plants need just to survive, right? We won't see plant growth with it, right? So they need a certain baseline, and that's going to vary depending on each plant, right? And it's typically not 0, right? They need some measure just to survive. Now, so this is a general growth curve, right? But then this is also going to vary based on plant species, right? Our plant species are all a little bit different. They have different requirements in terms of light energy and how they grow. And you can see here are two different curves that we have here. One is for lettuce, and you can see lettuce doesn't need quite as much or doesn't utilize quite as much light, right? It gets great growth, really maximum growth. And again, this is just drawn, so don't take it as, exact. But lettuce gets great growth at lower ppfd values, right? So not as much light intensity, right? You can get away with growing it under, if we're growing artificial lights, measuring something around 500 ppfd, you're going to get great growth. Now, cannabis, on the other hand, and corn is similar as well, that loves light, and you can really push it and grow it under higher ppfd values, and you're going to see an increase in photosynthesis. And really, we could use photosynthesis, net photosynthesis on this y-axis, but this could also, we can also use yield here, right? So as you're increasing your light intensity, you're going to see better yield, particularly for cannabis or plants similar to it like corn that really love light, right? So again, the importance of this ppfd value for our plants. Now, that ppfd is measuring instantaneously, right? It's the amount of light energy per second that is landing on, we'll say, our plant surface, right? Our plant's leaves. But what can we do? So that's per second though, right? But what we can do is take that value and turn that into a daily value, right? So it's kind of more important than just per second how much light is being our plants are getting. Really what we want to know is how much light are our plants, or how much light intensity, or how many photons are are reaching our plant over the course of a day. So what we can do is we can take this value and turn that into what we call the daily light integral, right? And that measures this photosynthetic photon flux density over the course of a day, right? And like I said, it's the number of photons that are being delivered to our plants over 24 hours. And here's the equation to do it, right? You take your photosynthetic photon flux density, you multiply it by 60 minutes that occur in an hour, 60 seconds in a minute, right? Because it starts out as seconds and we're trying to get it to hours, times how many hours your plants are exposed to the light. And then you want to convert that into moles instead of micromoles. So you divide by 1,000,000. The simplified version of this equation is you take your ppfd value, you multiply it by 0.0036, and then you multiply it by hours of light. And that's going to give you your daily light integral, right? How many, the amount of photons that are being delivered to your plant over a 24-hour period. And again, those photons are being used to power photosynthesis that are ultimately going to affect your growth and yield. So if you look in the United States, this is going to vary. Your daily light integral is going to vary by season, right? In the colder winter, you see where we are in New Jersey, right up here, we're going to have lower light integral values. Again, the day is shorter. The angle of the angle that the light is reaching the Earth's surface up here in New Jersey is steeper, so there's less energy hitting the surface, right? So we're going to have less photons per meter area. So you see we have lower values, right? And then you get closer as we heat up to spring, more the growing season, we see these values rise all the way up to, we get a maximum here, really 40, 45, all the way up to about 50 as a daily light integral, which is very high. Right? Close to it. We can get close to it. Okay. Now we can also measure this in a greenhouse, right? And typically the max you're going to see at a greenhouse is about 30 daily DLIs. It can vary as well. But what's important is we also have information on different species and their requirements for daily light integral. And you can see the more light that they get per day, right, is going to affect their quality. That is for a number of species. Here's a link that essentially is this chart expanded with many more species. And you can look at the minimum daily light integrals that you should be achieving in your greenhouse if you're growing these species per day to ensure that you have good or high quality crops. And now just to return to our cannabis example here and how you would calculate this, right? If you're growing cannabis, you're starting during its vegetative period. So what we talk about in plant science, and I'm not going to get too in-depth into here, but cannabis is a plant that responds to photoperiod, right? So some of our plants respond to photoperiodism, and that is variations in day length, right? It changes how they develop due to variations in day length. You can have long day plants and short day plants. And essentially what it is and what cannabis is a short day plant. And what that means is that when day length gets below some critical day length, right? When the length of day gets below a certain time period or a certain amount of hours, it's going to trigger our plants to become reproductive and start producing flowers, right? So with cannabis, that's around 12 hours a day, right? So if we were growing these out in a field, right, we're in the summertime and we're getting a lot of light per day. And as we start to get into fall or late summer, the day length is shortening, right? If we get to under 12 hours of light a day, it's going to trigger these plants to start becoming reproductive, start producing flowers. So if we are growing this indoors, right, or in a grow chamber, we need to be aware of that. And that's also going to affect our daily light integral, right? Because we're looking at our ppfd over the course of a day. So if we're having a shorter amount of time that our light is on, it's going to decrease our daily light integral. So again, if we're looking at cannabis, ideally, we're going to see as our daily light integral increases, right? We're also going to see increases in yield. Again, more photons, more light, more glucose, more growth. And ideally, you want to be growing them under around 1,000 micromoles or 1,000 ppfd, which is really high. But again, cannabis can handle that light. So how you would calculate this is if under the vegetative period, right? So that's when we're just growing it, not expecting them to produce flowers yet. You want to grow them at least 16 hours a day. If you're growing it at this high ppfd, you would take your 1,000 ppfd times that 0.0036, and then by the amount of hours a day that you're growing them, and you'll get your value of 57.6, which is very high, very, very high value for a daily light integral. It's a lot of light being that our plants are taking in, but again, certain plants can handle that. And then when you switch over to reproductive and you switch it down to 12 hours a day, you would calculate again, same thing, your 1,000 ppfd times 0.0036 times the amount of hours in a day, and that gives you a lower value, right? But again, still a high value. If you compare that to, most greenhouses are looking up at 30 as their max, right? It's very, very high value if you're growing indoors and you're trying to maximize the yield. Okay, so that basically covers light quantity, right, or the intensity of light and how that affects our plants. And if you go back to the beginning, we looked at those different wavelengths, and we saw those different wavelengths. We have different wavelengths of light, right? So then, knowing that we have different wavelengths of light, are they going to affect plant growth in any particular ways? And what we found is that when it comes to plant growth or yield, it's really more important the light intensity that we were just looking at, right? The ppfd value or the daily light integral. If we're looking at yield, right, or overall growth, that's more important than the particular colors that we are growing our plants under. Where color has a bigger effect is on plant shape. And we can see a summary of those effects down below, where blue light tends to inhibit cell expansion. So blue light tends to make our plants smaller or shorter. Green light is very important for human vision. And as we're going to see there, when you grow under blue lights or red lights, it changes your ability to recognize plant diseases, right? You can't see them because your plants are different color. So including green photons is actually really important to be able to make sure your plants are healthy as you're growing them. Red photons are very good for photosynthesis, right? As we saw, these are all get utilized for photosynthesis. Blue light gets absorbed more by chlorophyll, as does red light. Red light seems to be a bit more efficient in terms of driving photosynthesis, about 15% more, as we'll see. And then what we haven't touched on yet, but are far red photons. And we'll get into them a little bit here, but those are past that 700, right? That PAR range is 400 to 700. If we get past that 700, we start getting into far red or infrared light. And we see that that actually has an effect both on improving photosynthesis, which we'll look at, as well as changing the shape of our plant. And that our far red lights tend to make our plants taller, right? Our blue light is making them shorter. Our far red light is making them taller. And if you've had me in plant science, we talked about photomorphogenesis, which is that shade avoidance response, or at least that's the type that we looked at, is that shade avoidance response. And that utilizes those far red photons as an indicator that our plant is being shaded, and thus it needs to grow taller to get past that shade. So look at these a little bit more in depth. We'll look at some examples. All right, we said blue light inhibits cell expansion, so it typically makes shorter plants. Over here, this is cannabis, right? This is grown at 5% blue light. This is grown at 20% blue light, and you can see the height difference, right? Here is salvia. Again, as you go towards the right, we're seeing an increase in blue light, essentially, that is included, and you can see your plants get shorter. Again, here's another example with impatiens, right? As we increase the amount of blue light, we typically get shorter plants, right? So again, this isn't necessarily affecting yield so much, or dry weight of our plants, or potentially even like yield of crop, but it is affecting the plant shape. Kind of as I talked about, what I just alluded to there, talking about is it's not necessarily affecting yield or quality of crop if we're looking at blue light. Here is examples again with cannabis. If you look with flower yield under different percentages of blue light, we may see different shapes or different sizes as you see here, but it doesn't affect the yield, right? Ultimately, you're getting the same yield or flower yield under different fractions of blue light. And it may look like these numbers are going up, but if you look at these are standard deviations, that's the variation. You see there's big variation here. There's no real statistically significant difference growing these under this different amount of blue light in terms of yield. Or if we're looking at cannabinoid concentration, so CBD concentration or THC concentration, again, we don't see a difference growing under different percentages of blue light, right? And this may vary from what you'll see in some articles or lay articles that say it could vary. When they're doing the scientific studies, when they're doing the lab studies, they're not really seeing that difference, right? At least not a significant difference. That's blue light, right? Typically going to make our plants shorter. As I said, green, again, green is utilized during photosynthesis. We talked about earlier, it has that good ability that to transmit through our plants, right? Get into deeper tissues, get below the top canopy of our plant leaves. But green is also really important in identifying plant problems and diseases, as I talked about, right? Look, if you're trying to grow these plants, right, and you're growing them under red light, blue light, as opposed to natural, or we'll say a white light or white LED light, which is really a combination of these, right? If you're trying to identify common plant problems or diseases, you're going to have a really hard time doing it under these red light and blue lights because it gets washed out. You're not able to see them. So by including those green photons, you're improving your ability to diagnose any problems or growth problems in your plants, right? Even changes of color. You're not going to be able to see it under here. As you can see changes of color here and maybe indicating maybe a nutrient deficiency that you need to address. Growing them under these without those green photons, it's difficult to determine that. And now we're going to get to our red photons, right? Again, red photons are good color, good spectrum of light for photosynthesis. It seems that red photons or red light's about 15% better for photosynthesis than blue light. And if we got down to it, so you want to make sure that if you're, any grow lights that you're using, you have a good amount of red light included. And then what I haven't gotten to yet, but what is really interesting is, as I talked about, the effect of far red photons, right? These are beyond that 700 nanometers, and they enhance cell expansion. So they make our plants taller. You can see the effect here, right? If we're looking up at these different species that were grown up here, you can see grown under red light, and as you start including or increasing the amount of far red light, you see expansion of the stem, right? Our plants are getting, you particularly see it with your geraniums right here, right? Look at that inclusion of that far red light and how those stalks expand, right? And like we said, as I mentioned earlier, this is an example, even here with the coleus. This is that shade avoidance response. So when your plants are being shaded out under a natural forest canopy, just like green light is able to transmit through leaves, so is far red light, right? It's able to transmit through there. So under a canopy, if you're a small little plant growing under a canopy of larger plants, what's going to be with the light that is coming down and hitting you is going to be far red light, or at least a lot more far red light than red light if you were just exposed to the sun. So our plants use that as an indicator, and there's a whole process that happens based on this phytochrome pigment system. but essentially they're able to recognize when they're getting more far red light, kind of makes them think they're being shaded out, and then they're going to grow taller as a response to get above that shade. All right, so you see that here. You can see it down here as well. Same idea. They grew plants under different wavelengths of primarily blue, primarily green, primarily red. And then with each of them, they did just that. And then they did another treatment where they added far red light. And you can see the difference, right? Where in each treatment where they added the far red light, you see taller plants. So far red light will affect the shape of your plants, as we see here, right? Make them taller. But there's also an interesting effect that far red light has, and that is referred to as the Emerson effect by the guy who discovered it, named after the guy who discovered it. And what it is that when you add a little bit of infrared light, you see an increase in the rate of photosynthesis than if you just did the single color itself or the single wavelength itself, or just the infrared light itself, right? You see this synergistic effect where you get an increase in photosynthesis with a little bit of infrared light added to any of those PAR colors. And what's happening, the physiological process behind that is photosynthesis. The first part of photosynthesis is the light reaction. And during that light reaction, there are two important photosystems or protein complexes called photosystem 2 and photosystem 1. And this is in our chlorophyll. This is where, or in our chloroplasts, this is where our chlorophyll comes into play. And essentially photons or light energy come and they strike photosystem 2, and that causes electrons to excite in chlorophyll and then jump from molecule to molecule to molecule. And as it does this, it releases energy, and that creates ATP and NADPH that is later used to power the carbon fixation cycle, right, where we take our carbon and fix it into glucose. So this is the important first step of photosynthesis. So what's neat is it kind of runs in order from photosystem 2 to photosystem 1. Now, photosystem 2 is absorbing light primarily under 680 nanometers. So red light and below, this is absorbing that red light. It's exciting those electrons. They're bouncing, bouncing, bouncing. They're creating ATP, and that energy is then used to fix carbon or create glucose. Well, that's photosystem 2, and that bounces over, and then eventually those electrons hit photosystem 1, and there's another small electron transport chain, and that kind of ends the process. Well, at photosystem 1, that absorbs light at 680 nanometers and above. So if you're including your infrared or far red light here, you're getting a secondary energy boost from this photosystem 1 that's going to allow you essentially to enhance or increase your rate of photosynthesis. So that's really when you're adding your infrared, that's what's occurring here, and that's what's allowing your rate of photosynthesis to increase. Right, so that's referred to as the Emerson effect, and it's an important discovery. This was discovered, I think, a while back, and then it was almost like rediscovered later on. And because of that, some people are now promoting EPAR, or extended photosynthetically active radiation. Right. So if we go back to the beginning, we talked about PAR as being between 400 and 700 nanometers, and that's the wavelengths of light that are important for photosynthesis. Well, taking into account that Emerson effect, we know that far red light has that added bonus and that added effect. We now consider, or at least with this EPAR, really anywhere from 400 all the way up to 750 nanometers being important for photosynthesis, right? Because we're starting to recognize the importance of that far red light, both in its effect alone and with that added effect as part of that Emerson effect. The last thing I want to talk about is UV light. This is kind of the cutting edge, right? If we look at our PAR graph here, we kind of considered 400, 700 traditionally, and now 750. And this is just a measure of this. This is the measure of this meter. That's not actually the PAR graph. If I can go back real quick, it's a bunch of slides. Real quick to this PAR graph. This is looking at photosynthetic efficiency, right? So the ability of our plants to use these different wavelengths for photosynthesis. You know, it's not a direct cutoff at 400 or even at 700, right? we see that there was some sloping down here, so we can consider that this had some effect. And there's even some sloping over here under UV, right? And that's the cutting edge that we're looking at now, the effect of UV on our plants and plant growth. There's different types of UV, UVA, UVB, and UVC, with B and C being most damaging to our plants. It's similar, I believe they are also the most damaging to humans as well in terms of sunburn. Now, these UV lights have the ability to damage our plants. And if they're grown in the field, oh, these are par graphs right here. If they're grown in the field, you see that the effect of that UV is smaller on photosynthesis. And what is happening is our plants grown in the field are exposed to UV light coming from the sun. Again, about 2% of the sunlight is UV light. And they build up a waxy cuticle, and they build up resistance like sunblock to that UV light, because that UV light is damaging. So in the field, there's not a huge effect. But if you're growing in a growth chamber where our plants aren't exposed to UV light, and you add a little bit of UV light, you can see this increase in or use of that light for plant growth. And that's because they haven't built up that cuticle yet, so that UV light is coming in and they're able to utilize it. The problem is this light can easily damage your plants as well, so it needs to be regulated in very, very small amounts, particularly B and C. I think the stuff that I looked at, they said you turn it on for like seconds, and that's it. More than that, it heats up, destroy your plant. So, like I said, this is kind of the cutting edge. There's not a lot of data on it quite yet, but they're looking into UV light and how that may affect plant growth or plant yield over time. So that is it. I hope you guys are doing well, and I will talk to you later.